Good morning, everyone. At least good morning from Reno, Nevada. Welcome to the second day of the technical sessions for the EOS ESD Symposium. I'd like to just go through a couple of virtual meeting reminders in preparation for the day. If you would like to ask a question, please use the Zoom chat function. And we recommend that you turn off all apps except for Zoom for your optimal experience, for things to go well for you. And we recommend also having a strong internet connection. Hopefully that's available to you where you are at. Okay. The next item on the agenda is the year-in review. The title of the year-in review is electrical overstress in manufacturing and testing. The talk will be given to us by Vladimir Kratz. Vladimir is the founder and president of ONS Filter, a manufacturer of US-made high-performance EMI filters. Vladimir holds advanced degrees in electrical and mechanical engineering. He has 24 US patents and is an author of numerous papers about EMI, EOS, and ESD. Vladimir is a task force leader of SEMI-EMC standards and a member of the EOS ESD Association standards working groups, including the EOS working group. Let's turn our attention to Vladimir.
How do we do that?
Go ahead and click through your presentation, Vlad.
So my presentation is on your computer or on my computer?
We have
I can do it.
Controls of the presentation, Vlad, so just go ahead and click in that slide that says year in review. There you go.
Don't see that.
Now you are in the presentation slide that says TR23.
Okay, excellent. All right. Good morning, everyone. And today we'll be talking about the year-long the progress in our TR23 task force on EOS best practices. My name is Vladimir Kratz. I was on Filter, and if you have any questions on any topic in my presentations, please ping me. I'll provide the email address at the end of the presentation. So what is our mission? What we were working on during last year? So electrical overstress is a #1 cause of damage to IC components. Why do we know that? Because among other companies that stated that is Intel. Intel's manufacturing enabling guide was telling it to us for at least 20 years. So in the past, ESD Association were focused solely on electrostatic discharge, even though EOS is truly #1 cause of damage. And finally, within the last several months, ESDA promoted itself up to EOS ESD Association, putting EOS on its rightful place. So our document that we released, TR 23.0-91-20, is the first ESD standard document to solely focus on electrical overstress. Our TR23 group is quite diverse, which is a good thing because it gives perspective from many different angles. We have IC manufacturers, we have people who work on PCB assembly, we have equipment users, equipment manufacturers, and consultants. So, and the focus is on electrical overstress in manufacturing and test, and the task force is led by Terry Welscher and Nagdelmar Associates. And how do we advance to the next slide? Thank you. So what is the structure of TR23 document? It's structured to assist a broad range of readers, from complete novices who may be excellent in electrostatic management, but totally newbies to electrical overstress, to quite experienced practitioners, because in our documents, there is something for everyone. What is the structure? We cover sources, root causes of electrical overstress, categories of EOS exposure. We cover powered devices and unpowered devices. We'll talk about them all. AC, DC ungrounding, EMI measurements and mitigation, and EOS in automated test. Let's please advance to the next screen. So what are the aspects of EOS? Electrical overstress can happen at the different phases in the device lifespan. So let's take a look at this lifespan. I don't know if I have the laser pointer, but trust me, it's there. We start with upper right quadrant, unpowered device handling, which is essentially most of the device handling in IC manufacturing, and also in PCB assembly. Then we go to device test, which could also be considered a PCB test or product test. This is a one and only time device is actually powered.
There we go.
Then we move to product design, and then to final product application. And the EOS could be happening at every phase of it sometimes in a very different way. So we'll look at all of them and we'll also connect them with every step in our T23 efforts and document. Let's advance. Yeah, so let's start with the end, with device application. When I say device application, it could be either end user, or it could be, let's say, PCB assembly. Why so? Because PCB assembly uses devices as well. So user devices in already finished product in a field can expose it to a number of bad things due to quite a large variety of factors. Power surges would be AC or DC. What it means that you can have some rather interesting artifacts from AC power lines, or you can have a problematic DC power supply in your device or in your power adapter. Signal surges, excuse me, are often caused by induced voltages and currents from power circuits. And this is not always highly predictable. You plug your device into some other device, you plug into USB connector, you plug into Ethernet connector, and can have some interesting surges. Ground bounds. Most of IC designers, if not all, are quite familiar with ground bounds on IC. But now we will be concerned about ground bounds on a product level and on a complete product level. And those ground bounds could be quite significant. And those ground bounds could expose devices to quite high overshoot and undershoot voltage levels. Then faulty connected equipment. Your device, your equipment could be perfect, but then you plug into somebody else's equipment, and some other equipment isn't quite up to task, you may have electrical overstress from there. And there's so many other issues that a device in the field could encounter. Let's go to the next slide, please. So in device application, what can we do? Actually, very, very little, if anything at all, because use of product is out of control by a manufacturer completely. So the only thing we can do is to anticipate such instances and strengthen electrostatic electrical overstress protection in both on silicon and on a board level. This is quite problematic because not only it increases real estate on both silicon and on a PCB level, it increases cost, may cause signal degradation, and depending how it's done, it can even increase current consumption, which is in battery-powered devices is a fatal thing. So manufacturers need to make a judgment call on such extra field use protection. Sometimes you do nothing because this is what it is. And sometimes you have to. But what we can learn from failures and from EOS in field is to identify such EOS damage signatures and field returns and try to discriminate them from other types of EOS damage and from ESD damage, because this will give us quite valuable information on diagnostics and future design revisions. Let's move to the next slide, please. So what our documents say about it? Well, in short, nothing. Because finished product application are not controlled by either device manufacturer nor the PCBA supplier. And both of them are the sole focus of our TR23 document. We're not issuing this document to equipment user. So good engineering, like put in place reasonable overvoltage and overcurrent protection, both of device and on board level. And in case of industrial product, adequate instruction and product connections and integration is all that can be done. So why only industrial products? A couple of reasons. For consumer products, do you remember last time you carefully read user's guide of a product that you bought? It's number one. Nobody reads it. And number two, industrial users are far more literate and careful about their equipment use than consumers. And consumer products are often essentially disposable. So diagnostic methods that we provide in our TR23 document are very much applicable to understanding mechanism of EOS exposure in the field. So what it means that when you get a faulty product back, or failed product back, or damaged product back for your diagnostics, at least you can try to reconstruct what happened. So again, except for consumer products, this diagnostic method should help manufacturers and users of products to understand the reasons for excessive EOS exposure. As far as consumer products, however, it is important. Very few people care if your $10 device bought from Amazon fails. Let's move to the next one. So let's talk about product design. Again, we are kind of moving backwards on the whole chain, on the food chain. So IC manufacturers are concerned that product designers utilize their devices, put them in conditions where AMR, absolute maximum ratings, are exceeded. And I understand this concern. We had numerous conversations with different IC manufacturers on that. And so having designed both ICs and products for, I would say, mildly for several decades, it is very rare occurrence when an engineer designs a circuit which knowingly subjected IC to values above AMR or even approaching AMR. It really does not happen. It may happen in some small company where there is no what we call adult supervision by more senior designer. But honestly, I haven't seen any design during all my careers that does that. But what may happen is the device is exposed to over AMR values unintentionally, especially in a system design where separate parties are responsible for different parts of the circuit, but nobody kind of oversees the entire design, the entire product. And regrettably, this happens all too often. And this may have to do with on different levels. It could be a product that has several different PC boards connected in some way inside the product, and where essentially the only technical overseeing would be essentially product schedule, where different design teams work on different boards, but nobody technically oversees the entire thing. Or on a system level, it could be just as simple as, let's say, IC handler and IC tester. They're done by completely different companies, and yet they do work together. And this is where the EOS exposure could come in. So external to the circuit signals, there are not always checked for occasional unintentional overstress. So in essence, if you have designed your product or designed a PC board inside of a product, you would assume that all the signals are coming to you and all the loads to which your design sends the signal to are within specification. While the specification could be different for different parts of the system. So I would what I would encourage is to have somebody highly technical to oversee the entire design, or if part of the system is designed by a different company, work together. So now let's move to the next slide. So what could we do on a product design? Well, the mitigation may start with education, where IC manufacturers would utilize their datasheets and application notes to illustrate possible EOS exposure occurrences and how to anticipate it. And this is reasonably, from my point of view of IC manufacturer, is the only way to prevent such EOS, short of adding extra protection. If you look at any datasheet, at least absolute majorities that I've seen, you right in the beginning, you see the absolute maximum rating, and this is good. But it doesn't really go to enough details to assist a system designer to understand the implication of it. I would suggest that those who write datasheets for ICs elaborate a little bit more on the types of signals that could come to higher than AMR. In essence, provide a little bit more meat in your specification, so people who utilize your ICs would really understand it more than just a number. So maybe examination of specific failure signature on silicon may be helpful for IC designers and also for circuit designers, if such damaged signatures are somewhat unique for this case. Different companies have a different degree of complexity of libraries of damages. And I think it may be helpful for the industry to kind of combine them in one depository, short of any proprietary information, so people can learn from each other to understand the signatures of damage from electrical overstress. Let's go to the next one. So what our document says about it. TR23 document provides practical example of mitigating some of most typical AMR violation. Again, examples are not necessarily a systematic explanation, but it's a good beginning. So what can we do better? We can probably provide recommendation on a universal, quote unquote, way to address AMR specification that would include a short-term overload and other parameters that may be ambiguous. In essence, my message to IC designers is try to make your datasheet and application notes more explanatory to somebody who will use your IC without depth of knowledge in IC design. It shouldn't be that difficult. Then what we also can do better is provide more of an education section on board the system designers on various AMR perils that are not clear from the specification. And perhaps a separate upnote like a technical report on deciphering AMR for designers of boards and system with eye on EOS exposure. Again, everybody, including myself, are guilty of viewing any subject from point of view of your own expertise. Well, for IC designers, having been one before, my message is don't assume that circuit designers know your silicon or know IC design at all. And just like IC designers may not know in all the details the board design, the circuit design. So please be more explicit and detailed when you do the specifications. Device test. This relates to bare semiconductor device and to also PCBA test, because we'll consider this a device as well for now. So even the most sophisticated tester, would it be in-circuit tester, would it be IC tester, would it be functional tester? It can expose devices to electrical overstress. Causes can be hardware caused or software caused. Could be power or signal spikes, could be commutation spikes, could be ground bounce, power sequence errors, and so on. So device test, what can we do on a device test level? Well, this is the only time the power and signals are applied to the device while they are in manufacturer's custody, meaning that the manufacturer can control EOS and make changes to mitigate it. As we discussed before, when your final product in the hand of a customer and the hand of an end user, there is nothing you can do, it's too late. But while device is in your possession, you have full control over it. And when you apply power to the device, this is the only time you can actually do it in the whole device cycle. Whether it could be a wafer test, start from the wafer test, it's the first time the signal is applied to silicon. Could be package device test, like IC test, module test, PCBA test, finished product test. It is all still within your control. So what it means that if something happened, it's not only your problem, it's your fault, but also the good part of it is you can fix it. So what could be done? Well, a careful examination of every step in a software. Why should we concern? Why our EOS ESD association, we don't do software? Well, this time we made friends with software people. And we'll talk a little bit more about it. So we need to worry about actual measurements of signals and power applied to the devices during a real life test. Not just this what it's supposed to provide, but what it actually does. You need to get dirty with your scope or spectrum analyzer. Scope is better because time domain signals, and see what is actually happening, not what's supposed to happen according to specification. Just like many companies do with ESD, certify your process and certify your tools for electrical overstress as a separate step. And if your specific device would be, I'm sorry, a device, but let's say IC tester or any other equipment that you use is capable of providing excessive electrical overstress, don't use it until you fix it. Once you fix it, put a little sticker that is now certified, and once in a while, give it a good check. And also what we can do is to have close cooperation between device and PCB manufacturing, because communication could be quite powerful too, because IC manufacturers seldom know what circuit designers do. And the circuit designers may not know all the little things that are not necessarily pertinent to the guts of the silicon, but what threats could be present for silicon. So what our documents say about it? So the document contains detailed section on power sequencing, on test condition best practices, both for devices and on a PCBA level. And the teaching by example is one of the most effective hands-on strategies, because teaching fundamentals isn't really a practical option with the constraints of the document. Keep in mind that everybody has a specialty, and people on production floor and people who write the software for tools, people who design production tools and manage the process, mostly very, very good in what they do. They may not be really good in identifying electrical overstress. I mean, this is why there is often an ESD, separate ESD engineer or ESD group dealing with that. So trying to teach manufacturers at large about intricacies of electrical overstress and its basic physics, it's a nice thought, but it really doesn't happen. People don't have time for that. They need to produce millions of ICs in a very short time, as they need to ship out the products. This is not their main task. So fundamentals is good for a dedicated group. They're not very practical for the company at large. So teaching by example is, in my opinion, is much better practical step, which could be followed by fundamentals for some people. And so to make it more actionable, this section in our TR23 document may be greatly enlarged and detailed. And we kind of slowly working towards that. So the challenge is to make this document a required reading for those who are not normally within ESD ecosphere. Test engineers, both hardware and software, who don't even know about ESD standards and frankly don't much care. And this is will be a challenge for EOS ESD Association standards for the future for every document that would deal with electrical overstress, because it deals not only with the static but with parameters that has nothing to do with ESD, but have to do with design of equipment, with maintenance of equipment, and with the software. What does TR23 say about automated testing? It provides the following recommendations. It recommends filtering of DC supply to device under test, including a simple solution as adding capacitors, which is not obvious to tester designers. Specifying order of test routines, including current and voltage source and compliance, test program hierarchy, test program validation, and strong recommendation on test parameters drift analysis. Here is an example from our TR23 document. Thanks to Alan and other members. Sometimes correcting EOS exposure threat is so much simpler than ESD threat. And here is an example. For example, so in this particular example, let's say if you plug your board into the, let's say, test socket, and all the signals are supposed to be connected theoretically together, which they never do. Signals could come before VDD, and or even worse. And what might happen is a nice latch up and device could be damaged. What could be done is, like on the lower bottom part, just change the configuration of a connector, which will connect your power first and then will connect the signals. The cost of doing that is very minimal and it's one-time expense. And in this case, return on investment is incredibly high. And this is a typical example for many of EOS mitigation threats. Unlike ESD, where each individual step has huge variances for a static charge and possibility of discharge, with EOS, it is much simpler because of a highly automated process. That means it's repeatable. And in many cases, return on investment is quite good. Let's talk about unpowered devices. That means everything that happens before IC test or before functional test or before in-circuit test, which is a majority of life of device in manufacturing. It's like 90% of it, if not more. So every step in device handling can expose a device to or PCB to EOS, anywhere from wafer through PCB assembly. Intentional signals and power are not a factor, because at this point, we're not supplying any signal to it, at least not nominally. Voltages and currents on ground are not that anybody plans to have. Ground is considered to be safe, quote unquote, for the devices. And for ESD, it may be. For high frequency signals, which called EMI, low ground impedance is not an assurance of no or low EMI signal. If anybody curious, like 4 years ago, I did a paper together with Jeff Salisbury on how it was 0.2 ohm, if I remember correctly, it was 0.2 ohm ground connection. We had more than 1 volt EMI signals on ground, and this is not good news. Having another threat is having device contact two different grounds, and this is a consequence of that. Even through capacitive coupling, not necessarily galvanic, can expose to EOS. And according to some studies, unpowered devices are more prone to EOS damage than a powered one. If you're interested, ping me and I will send you the interesting paper on this subject. So what can we do with unpowered devices? We can perform complete EMI control within the process, because again, in unpowered devices, EMI is the #1, if not the only source of electrical overstress. Our document offers insight into many processes in IC manufacturing and PCB with hands-on illustration of measurement and mitigation. It's actually quite elaborate document in this section. So unlike ESD prevention, EMI prevention requires no maintenance, just like what I just showed in a previous example with the configuration of connector, offering very low cost of ownership, meaning high return on investment for manufacturers versus ESD. The major problem that I consider that we still haven't done, but I hope we will do with our document, is we do not yet offer a recommendation on acceptable level of EMI, because there is no such thing as no EMI. Other industry standard organizations such as SEMI, where I am a member of SEMI Standards, and IPC, they do offer such limits. If you're interested, again, ping me, I will share some numbers with you. And I hope that our work group will either offer its own harmonized limits or adopt established industry recommendations. Because the problem is if you don't know your limits, you don't know how you're doing. You don't know that you're done. Once you're done, you have no goal. So what does our document say about it? Well, both quite a bit and not enough yet. So this section on power devices is perhaps the most comprehensive one in the document. And we provide plenty of examples of EMI-caused EOS. There are no other known EOS sources for power devices. And examples of mitigation. The document provides clear recommendation on measurement techniques and instrumentation for measuring EMI. And there are examples. Let's talk about these examples. So the examples of EMI-caused EOS exposure in our document are EMI on AC mains, EMI on ground, EMI on USB ports, EMI on automated equipment caused by servo motors, by switched power supplies, from LED lighting. You thought that this vision system in your AC handler is cool. Now it's very noisy sometimes. And EMI from commutation, I mean switching. The EMI measurements are a new thing for many of ESD practitioners. Therefore, a special effort was put forth to explain the details allowed by the document format. So emphasis is made on measurements, relevance, and their practical aspects, because there are many ways to do these measurements, and some are more elaborate than that lead nowhere. Among others, the examples are time domain versus frequency domain versus broadband measurements, voltage versus current measurements, safe measurements of EMI and live power using EMI adapters, because you have to do measurements in equipment as it works, because this one it provides most of EMI, so you need to be careful. And measurement of EMI caused EOS in soldering process. So we have a couple examples. So here is example in soldering process. See if I can have laser pointer. Nope. Sorry. Okay, you will have to trust me on that. I don't see laser pointer here, at least none that I can recognize. But what you see here on upper chart, in blue, in a purple or magenta, you will see the EMI spike on power line. And in blue is a current from the tip of a soldering iron to the device. So for those of you who manufacture soldering irons, please don't worry, it has nothing to do with your irons. Absolute majority, if not all, of professional soldering irons are quite good by themselves, but facility power and ground aren't. And once you plug your wonderful soldering iron into a noisy power and ground, guess what happens? You may have a lot of interesting spikes in your device. And when you install such mitigation means as a, let's say, soldering filter here, you will see now in lower bottom, you will see again in magenta or purple, the same noise on mains, but there is essentially no current going from the tip of your soldering iron to the device. The cost of maintenance of this, unlike SD, is essentially zero. Let's go to the next one. EMI on ground main is not the only cause of EOS exposure in automated handling. So, and difference in voltage between two different ground points. Again, ping me if you need the papers that I did together with Jeff Salisbury on it. It could be quite high. So in every ground wire inside the tool, just install ground filter. And this is a current without it, and this is in magenta, and in blue is current with a filter. And you have fully compliant ground connection and no EMI. Therefore, no electrical overstress. Power lines in any facility are quite noisy. Some tend to blame them on incoming power. This is not true. Most power companies provide reasonably good quality power. It is all the equipment and the facilities that goes ka-chunk. And every time it goes ka-chunk, you have spike. And the spike propagates through facility power and ground and creates problem for equipment. Not only actually for electrical overstress, but also interferes with the test. And by, again, if we go to Intel recommendations, number one, install power line filters, and then your equipment is essentially noise-free as it shows here. Again, cost of maintenance of it is essentially zero. So our EOS standards is still work in progress. So TR23 document is just the first document of EOS within ESDA. And a lot of work remains until we address EOS in comprehensive and actionable way. Challenges include kind of going outside of ESD specific boundaries, re-education of ESD practitioners. Assessing and mitigating EOS requires different skills than to possess an ESD. It's not very difficult, but it's different. For example, device and PCBA test, quality of power supplies, commutation artifacts, signal power sequence, etc., not governed by ESD. Why would a test engineer read EOS document? How would an engineer translate EOS exposure into actionable control? And this is a challenge, not just of our group, but overall our standards, because we need to make sure that our documents propagate throughout the factory, not just to a very narrow group of practitioners. And dealing with EOS is a group effort. It cannot be mitigated by any one group at the factory by itself. It is a collective task. So our challenge is to widen our normal kind of ESD focus horizon and engage broader multidisciplinary audience. Because overseeing electrical overstress on a factory level has to be done by higher level management that governs all of these groups. And factory level education about EOS is critical. So going forward, our first document is just the first step in a kind of 1,000 miles journey. And this journey may eventually culminate in a 2020-like document, providing comprehensive guidance to assessment and mitigation of EOS. And such documents may have recommendation on acceptable levels for EOS. Without numbers, there is no target and no action plan and no criteria of success and no assurance of EOS safe process. The good news is the TR23 has a good cross-section of experts from different aspects of industry, and we are up to it. And this is my end of my presentation. Thank you for listening. If you have any questions, ping me and I'll be happy to provide answers to the questions I have. So thank you very much.
Thank you, Vladimir.
And unfortunately, we have run out of time for Q&A, so you can contact Vlad directly for your questions.
Thank you. So the next thing up is a break, and we will be breaking until 9:10 a.m. Pacific Standard Time, or Pacific Daylight Time. So you are dismissed for the break.